Okay. So we were at the point that we were talking about this hierarchical model with a full variance covariance structure, right? So this was this model. And one thing I want to ask you guys before we proceed any further is whether you have any questions about how this hierarchical model is assembled. Any questions at all? It's very important that you're clear on what's going on with this model before we go any further. I hope that the silence means that everyone is clear.
I have a small question actually.
Yes, please.
About the notation there, and it got me a bit confused.
Okay.
So the variance component itself comes from a normal distribution, right? And it also has another variance component, sigma. Both of them are sigma, so I got a little lost here in the second line.
The second line, right?
Yes.
So this, oh, sorry, did I mess this up? I'm so sorry about this. Hang on. Okay, that's just a typo. Let me fix that. Hang on. That, of course, that is nonsensical, what I've written. So let me fix that. What I wanted to say, okay, so let me just fix this. Okay, let's do this right now, because then again, I will make this same stupid mistake. And where we have, okay, so this is much better. So basically, what I'm going to do is of course, I'm not going to have a normal 0 sigma prior on sigma. I cannot reuse sigma twice. That's a very good observation, right? So this will have to be some constant value, right? So this is called, the parameter that I will put here will be called a hyperparameter. Okay. And so because this is a parameter on a parameter, right? And that parameter that I will put in here will represent the amount of variability I allow in sigma a priori. Okay. So let's see when this thing finishes. It's still compiling. So as soon as it compiles, we will get, let me just reopen this file. Okay, so here we go, right? So if I reopen this file, it should have corrected. So what this should be is a truncated normal, obviously, right? Pratik? Whenever I define a prior on a standard deviation by definition cannot be less than 0. Therefore, even if I write normal, it means a truncated normal. Are we good?
Yeah, yeah.
Very good. Thank you. That's a good observation. That was a very stupid thing I did. I made a mistake there. But nevertheless, the important point is that there are, how many variance components are there? There's the residual standard deviation, sigma, that goes into the log normal likelihood. Then there are the two variances for the subjects, two variances for the items, and the two correlations. How many parameters in total? Intercept, slope, sigma for the residual, that's 3. Then 3 in the variance components for subjects, that's 6. And 3 in the variance components for items, that's 9. Okay, so I have 9 parameters in this model. Now, I'm going to have to estimate the posterior distributions of all those parameters, and therefore I'm going to have to define some priors on them, right? So that's what we were talking about when everything crashed. So for the intercept and slope, I had a normal 0, 10 prior for the intercept because I want to allow reasonable amount of variation in the intercept. I don't want to give a very precise prior. On the slope, I have a normal 0, 1 prior, which is actually also very vague. Okay, on very vague prior for the effect of the relative clause. The effect of the relative clause will be represented by this beta parameter. And I will show you what happens when we actually interpret this parameter. Then we have the residual, standard deviation, and all the other variance components are also normal, 0, 1, truncated. The place where I stopped last time was I was talking about what correlation to define what prior to define for the correlation parameter. So that's what I'll talk about next. Okay. So let me talk about this point. So in order to do this, I'm going to have to pull up my iPad and just connect to the iPad. Mirroring. Just a second. Okay, so now I'm having new problems with this thing. Never mind. So what I'm going to do is I'm going to define a prior on the correlation parameter. And in order to do that, let's think about it. Okay, what could be a possible range of possible values for a correlation? What are the possible ranges? Upper bound and lower bound.
From -1 to +1.
Very good, right? So that's the only possible support I can have in the probability density function that will define my the prior for the correlation, right? And so what I'm going to do is what I want, just jumping ahead a little bit. Intuitively, what I really want is a correlation that looks like this. Can you guys see this? Make this a little bit bigger. This is the rho parameter. I want a correlation, a prior on the correlation that is regularized. What that means is that this prior should have the property that +1 and -1 should be very heavily downweighted, and the intermediate values should have a higher value. What this prior states, the interpretation of this prior is that I'm going to be agnostic a priori about possible values of the correlation. I will allow a wide range of variation, right? So it's not a very informative prior, but I will regularize the distribution such that the extreme values are downgraded. This is a very, very important moment for us because this regularization will guarantees that our hierarchical model will converge. We will never get a +1, -1 correlation like we used to in the frequentist model, in the Elmer model. That will never happen. Why? Because the prior rules it out a priori. Okay, it's a very important moment now. So this thing is a game changer for us because this prior. But now the question is, how do we define such a prior? Well, it turns out that in Stan, there is a very interesting prior that is available, and that prior is called an LKJ prior. LKJ is the name of, sorry, what have I done here? LKJ is the name of the, they've over-engineered this computer so much, it's just absurd. I've switched to Japanese for some reason. Just one second. Right, so I'm coming back to sharing. Right, so for the correlation, there is a special prior that's available in Stan and in BRMS that defines that shape, that distinctive shape that I showed you. That's the shape that it will define. And again, I've gone into the same problem. Need to disable these languages somehow. Okay. Okay, so the LKJ prior will be defined on the correlation, and more specifically, what we're going to do is what Stan and BRMS does is that the LKJ prior is actually defined on something called the correlation matrix. Now, the correlation matrix is actually implicitly present in the variance covariance matrix, right? So if you think about the variance covariance matrix, what does it contain? On the diagonals, it contains the variances. On the off diagonals, it contains the correlations inside the covariances, right? The off diagonals. So what we're going to do is that using one fact, we're going to use the following fact. What is happening now? This thing has stopped working. Yeah. All right. We're going to use the fact that the variance covariance matrix can be decomposed into 3 component parts. You can actually break up this variance covariance matrix into the standard deviations and the correlation matrix and reassemble the variance covariance matrix. This is a mathematical fact, and I'll just show this to you. Yeah? So let's go to the next slide, right? So what's going to happen is that we will define a prior on this matrix, which is called the correlation matrix that corresponds to this variance covariance matrix, right? So the reason this is called a correlation matrix is that on the diagonals, you see the correlations of every random variable with itself, right? So that correlation has to be 1 because every random variable is perfectly correlated with itself. So that's why the diagonals have a correlation of 1. The off diagonals contain the correlation between the random variables in this bivariate example, right? So this is called the correlation matrix, and we can define a prior on this matrix, right? And the reason we can do that is that once we define a prior on the correlation matrix, and once we define a prior on all the standard deviations, we can use the fact that you can assemble the variance covariance matrix from the standard deviations and the correlation matrix and get back the variance covariance matrix, right? So in STAN, what we do is when we want to define priors on the correlations, we first break up the variance covariance matrix into these 3 parts, define the priors on the correlation matrix, define the priors on the standard deviations. I showed that to you earlier. And then reassemble the variance covariance matrix by doing this matrix multiplication that I'm showing you here, right? So if you guys are familiar with matrix multiplication, what we do is we take to multiply these matrices, what I would have to do is I would have to multiply this row with this column to get the product here. So it would be sigma u1 multiplied with 1 plus 0 multiplied with rho u. So that would give me sigma u1 here, right? And so on. And then once I've done this multiplication, then I would multiply that entire result with this matrix. And you can confirm this yourselves, right? You will eventually end up with the variance covariance matrix right there. All over again, you'll get it back. Amazing fact, but true, okay? So what the bottom line is, we've defined the priors on the sigmas, we defined the priors on the correlation matrix, and we know how to rebuild the variance covariance matrix. This is exactly what STAN does actually inside, underlyingly inside when you look at the source code. Okay, so we are all set. All we have to decide now is what kind of LKJ prior we will use. So there are different parameters that you can set for the LKJ prior. When you set the parameter is called eta, ETA. Okay, it's a Greek letter. So if you set the parameter at 1, you will get a prior that is just like a uniform prior on the correlation parameter, right? So it will allow all possible values between -1 and +1. That is not something that we ever want, right? Because intercepts and slopes are very unlikely to be perfectly correlated. They would be maybe 0.5 at most. And that's why we will set the eta parameter not to 1, which corresponds to the uniform distribution, but to this regularizing prior that downweights the extreme values, right? And the parameter that gives that downweighting is 2, right? You can use 2 for that. If you increase the parameter, you get tighter and tighter priors on the correlation. So you can have informative priors on the correlation matrix, of course, right? Okay. So basically that's it. I mean, we are ready to roll now, right? So all we have to do is first make sure that we visualize our priors so we know what they look like. This is the intercept prior on the log scale, slope, all the sigmas. Here are all the sigma priors, and then there's the correlation, right? So we are all set to start modeling now. And how do we define the priors in BRMS? That's pretty easy, right? There's the intercept, define the normal 0, 10. Slope, the slope is called SO because I defined a column, right, with the +1, -1 coding. That was my predictor, right? So whatever you call your predictor, that's the name that's here, right? And so this has a normal 0, 1. All the other standard deviations, the STs are the standard deviations of the variance components other than the residual. The residual standard deviation is a special name, and that is sigma, Okay, so sigma has a normal 0, 1, and the other standard deviations have a normal 0, 1 prior also, truncated, of course, right? So you have to remember that in this kind of linear mixed model or hierarchical model, you have to define the priors for all the standard deviations other than sigma and the prior for sigma as well. You can't just define one prior. If you don't define a prior for sigma or for the SDs, then probably BRMS will choose some default prior. You remember that student T prior with 3 degrees of freedom? That's a little bit too liberal in my opinion. So I wouldn't use that, okay? And then finally, for the correlation parameter, right? For the correlation matrix, we're going to define an LKJ prior with standard with eta parameter 2. So that's that regularizing prior that I just showed you earlier, right? This
Can I
regular,
ask
yeah.
one or two questions?
Go ahead.
So I guess my first question is on the previous slide you were just showing that had where you were setting the priors. So I know that it's the prior on the like sigma is a truncated normal because it can't be negative, but where is that reflected in the code? It seemed like it was just saying it was a normal prior.
Very good. Yeah. So BRMS, if you, yeah, that's the right question to ask. So if you look here, it doesn't say anywhere that this normal distribution is truncated. What BRMS internally does for you is that whenever you define SD, standard deviation, or sigma as the type of the parameter, then it will internally truncate it for you. Later on, so later on in this book, if you read the book further on, if you go into the stand coding chapters, you will have to define those priors yourself, and you will have to correct the area under the curve. You know, like I showed you, when you truncate the prior, you have to make it into a proper PDF. You will do that by hand when you type it in stand. But BRMS is conveniently doing this for you, so you don't have to think about it. Okay?
Got it. Thank you.
Yeah.
And then I guess my other question then was, is LKJ, what does that name come from? Is that like an acronym for something, or what does LKJ mean?
LKJ is the name of the 3 authors who wrote, the initials of the last names of the 3 authors, Lewandowski, someone and someone. I don't remember the other guy.
Fair enough. Okay. Yeah. Got it. Thank you.
Yeah. So they came up with this great prior. You know, the beauty of this prior, you have to appreciate this. Like when you're fitting models that have 8 by 8 or 16 by 16 variance covariance matrices, this does happen. Okay, when you've got these complex models, you just define one prior on the entire correlation matrix. So if you have 16 random effects, you got 16 by 16 variance. When you have how many random effects? So let's say if you have 15 predictors, you will have an intercept plus 15, and therefore you'll have a 16 by 16 variance covariance matrix, right? And in that situation, you'll have a 16 by 16 correlation matrix. You just define one prior on the entire matrix. It's amazing. So I want to tell you that in 2011, when I was fitting Bayesian models for the first time using JAGs, I was just trying to fit a 2-condition design, just like this one. And I was having so much trouble trying to define the priors on the correlations. I could do it for a 2-condition design, but for a 4-condition design, it was very hard to figure out how to define a prior elegantly for all the correlations. And like the methodology that they provide in JAGs and WinBugs is, I think that they choose an inverse Wishart prior for the covariance matrix. And that just didn't work for me. Like I just couldn't compute the parameters in that complex matrix. But in stand, it's a breeze. So this has been a game changer for us because it has made it possible for us to fit extremely complicated models, right? Very, very sensibly using these kinds of LKJ priors. Because we always want to assume, just like Barr et al. Recommend, we want to assume that there's the possibility of a correlation. Even though there might not be any evidence for it in the data, we still want to a priori assume that there might be. So we want to include these correlations. And we can do it no matter what the model. So you should look at Paula Lisson's models. Her PhD work is on her homepage. Take a look at those models. Those are unbelievably complex models. These are cognitive models, of language processing. But she can define any, relationship that she likes in those models. So it's a tremendous capability now that we have. Any other questions on the priors?
So I have one actually.
Go ahead.
You showed us how the LKZ prior or the metrics can be decomposed, right? And then, but in this BRMS syntax, we just define like LKZ2, but I could not wrap my head around in that mathematical notation how this 2 goes in, right? Where it fits.
Yeah, the true is only ensuring the shape of the prior on the correlation, right? It's an internal. This is what you're seeing on the screen right now. This is syntactic sugar. Okay, so basically, it's what you're stating. You know, when you write that LKG2, you are stating declaratively what you're saying is that I want a regularizing prior on the correlation that has the shape that I showed you earlier, right? It has to have this shape. That's what you're stating. Now, your question is, how does this work in detail underlyingly?
Yeah.
Underlyingly, the story is much more complicated. Okay? Underlyingly, what you will do is, if you're writing stand code, you will define a prior on that matrix, on the correlation matrix, and then you will actually multiply out these matrices inside the stand code to reassemble the variance covariance matrix.
So in a stand code, basically I would be defining prior for each and every component, right?
Oh, yes.
But here in BRMS, it made us easy that we just say LKZ prior and a certain number. That's the difference, right?
Well, there's more to it than that. So I don't know if I want to go into this right now. Let me see. Let me just pull up the book, just a minute. Right, so let's take a look at this book for a second, just a short digression, just to look ahead to what is coming later, you know, in this course. Not in this course, but if you study Bayes in more detail, if you look, for example, at right, let's look here. This is a good example, okay? Yeah, this is the best example to look at now, right? Okay, so here's a very similar situation there to what I was describing to you guys earlier, okay? I've got intercepts and slopes, and I've got some predictor. In this case, it's centered close probability, right? The model is just like the same one that I showed you. The priors are somewhat different for the standard deviations because that's an ERP study now, but the correlation parameter is the same, okay? It's the same as before. So what's going on underlyingly? Let's look at the stand code, okay? I'm going to show you now. Now, don't complain because now it's going to look really difficult because the underlying machinery is complicated, right? So what's going to happen now is that, see, I've got a diagonal matrix for the tau u's. What is tau u? Tau u are the standard deviations for the subjects, okay? Oh, sorry. Yeah, tau u1 is the intercept adjustment standard deviation for subjects, and tau u2 is the slope adjustment for subjects. Okay, so and tau u1, u2 is there, then tau w1, w2 is there. So take a look at tau u. Okay, tau u is actually a vector. Can you see this? In this code, tau u is a vector containing the standard deviations for the intercepts and slopes for subjects. And what I do is I'm actually multiplying it with the square root of the correlation matrix. Okay, so that's called the Cholesky decomposition. The square root of a correlation matrix is called a Cholesky decomposition. So I'm gonna multiply those two guys out, and then I'm gonna multiply it with a standard normal, and this will end up giving me the intercept and slope adjustments by subject. I do the same thing here. It gives me the intercept slope adjustments by items. But if you look here, where are we? Let me see if I can find my, here, look here. So this command here is saying that take the square root of the correlation matrix, that is the Cholesky decomposition, and assign an LKJ prior with parameter 2 on that matrix. Okay, so this, what I've done is I've got a prior not on the correlation matrix underlyingly, but on the square root of the correlation matrix, the Cholesky decomposition. So that's what's happening in, I mean, behind the scenes, right? And then what you do is that you can assemble from that information, you can assemble the variance covariance matrices, right? So the variance covariance matrices turn up here. So look, this statement here is actually saying that the dependent variable, which is called signal, is generated from a normal likelihood with alpha intercept subject adjustment to the intercept, item adjustment to the intercept, and then there's a predictor multiplied with this fixed effect slope with the slope adjustments by subjects and the slope adjustment by items. Sigma is the residual standard deviation of the normal likelihood. And look here in the generated quantities, I'm assembling the correlation matrix for me to look at, if I want to look at the posteriors of the correlation matrix, I'm taking the Cholesky decomposition, that is the square root of the correlation matrix, squaring it by multiplying it out, and I get the correlation matrix back. So I can look at the posteriors of the correlations now, right? And so where did I assemble the variance covariance matrix? So I don't directly assemble the variance covariance matrix here. So what I'm doing is that I've got the vectors for the subject standard deviations and the item standard deviations. I've defined a vector of length 2 for each of those, and those are actually determining the intercept and slope adjustments U and W, and the correlation between the intercepts and slopes is happening in this line. In this line, I am multiplying the standard deviation with the square root of the correlation matrix. That's what gives me the correlation, because the correlation is inside the square root there, right? So this is why I didn't want to talk about the underlying machinery. It's ugly, okay? It's ugly if you're not familiar with it. Once you're familiar with the Cholesky decomposition, it's easy, right? It's just pretty automated. Now, BRMS makes this really easy for you, right? They don't want you to think about this because in 99% of the cases, it's all going to be pretty standard coding, right? You don't have to keep writing this over and over again in Stan. And in fact, when I write Stan models that are hierarchical models, I just have one file which contains one piece of code. I just keep reusing it for any model because the underlying data is all that is changing. The model remains the same, right? Because I define my models in matrix form. And if I have a model matrix, I can do whatever I like inside that model matrix. So that's something I will discuss at some point if we get a chance. But right now, the easy way to fit these models is by defining these priors. And then fitting the model is now trivial, right? All I say is with BRM, I say, I'm going to use a log normal likelihood. Notice that the dependent variable is not log RT. It is RT in milliseconds because that's what the log normal produces. It produces the exponentiated data. And so this is my maximal model, the so-called maximal model with the log normal likelihood and the priors. And that's it. I fit my model and I can look at the posteriors, right? And so I've got, this is the parameter of interest, and you can see that it's largely positive, you see. And so from this, what people would conclude is that they can argue that the object relative is actually harder to process than the subject relative, as expected, right? And these are all the variance components that you can see for the standard deviations and so on. And here are the correlation variance components. So these are interesting to look at. First of all, look at the subject. This is the subject intercept slope correlation, right? So this is very interesting because it is positively skewed. Can you see that? It's all positive values. And so it seems that the correlation is around 0.5 here, but there's a lot of uncertainty on this. And the reason there is so much uncertainty is because we have only 42 subjects and only 16 items. If we could run an experiment with 400 subjects, right, and let's say 64 items, we would get a tight estimate on the posterior. Right? So there's not much information in this correlation, but it's you can actually estimate it. Now look at the items correlation. This is the item intercept slope correlation. What do you notice? What's the difference between the subject and the item correlations? Take a look and tell me what you think the difference is. Any proposals?
It is not so heavily skewed to the right as the subject correlation.
That's correct.
And the uncertainty is even bigger. It's ranging from -1 to +1.
Exactly. So the most interesting thing about this correlation parameter for items is that it's ranging from -1 to +1. Why do you think it has that shape?
Because there's not very many items, so we don't have much information about how the population of items, individual items in the population of items differ from one another.
Exactly. So this posterior for the correlation that you're seeing here is heavily influenced by the prior, by the LKJ prior. That's why you're seeing this distinctive regularizing shape. Now, if I fit this same model in Elmer, you know what would happen? For the subjects, it would give a correlation of 0.5, but for items, it would give a correlation of 1 or something like that. That is a convergence failure in Elmer. It's unable to estimate the parameter because there's just not enough data, right? But for us, that's not a problem because the prior will take care of the parameter if it's not, if there's not enough data. Okay, so that's pretty simple now. Okay, so yes.
Just a quick question. That range, the huge range of correlation, does it affect the estimation of fixed effect, or should we keep that correlation, that particular correlation?
So it will not have a big impact on the main parameter of interest, which is this subject object parameter. This will not change very much. Okay. So you could actually remove these correlations and still get a decent estimate, a similar estimate, sorry. So let's see, we are from 0 to 0.14, right? So let's try it. This could be fun. Let's do this, okay? So where's my model? Let's see what all I have already. Okay, very good. So I can now try to fit this model. Define my priors, right? And so what you're saying, what you're suggesting is to drop the correlations. So I'm going to drop this correlation prior, okay? I can't actually fit the model with a correlation prior. There's no correlation in the model. Are you with me? You understand this?
Yes.
Okay. So I've removed that, and now I'm going to change this model such that it only has intercepts and slopes, but no correlation. So basically what I'm assuming now, a priori, okay? Let's be very clear about what we are assuming. What we are assuming is that we have the same model as, the same model as before. We have the same model as before, but we are assuming that these rho U and rho Ws are 0. They are point values for us. That's what we are assuming now. Okay? That's an explicit assumption we're making. So let's see what happens when I fit this model. Oh, it still thinks that, did I not run that command? Let me just try it again.
I think there is a comma at the end. That shouldn't have been there.
Thank you. Yeah, I didn't notice this. Yeah. Okay, so now it should work. So when I fit this model now, what we want to know is what's the difference between this model, the posterior on, whatchamacallit, the slope, and the, how does the posterior change? Okay, so we're going to focus just on this posterior as a function of removing the correlations. So let's see what's happening. It's still running. I'll let it run for a second. I'm just going to go get some water. Hey, are we done? Oh, there's some complaints here that we can fix that later. Let's not worry about that. But I want to see what the histogram looks like. Okay, so take a look. First of all, the correlations have disappeared as we would expect. There's nothing there now. The interesting thing is how much different is this posterior relative to the full model that we had fit. So let's try to put them side by side. Can we do that? Yeah. So this is my correlation, and let me see how I can do this. I gotta move this guy away. Just a second. Oh, there's a comment here. Sorry, what's happened?
Oh, I was just wondering, because I noticed we didn't specify the
Yes.
chains iterations warm up. So does it just do a default for that?
Yes, it has 2,000 iterations and 1,000 warm up. And
Okay, so like what we were doing yesterday?
yeah.
Yeah,
And
okay,
so,
cool.
yeah, exactly. So I should have done it properly, but I was in a hurry. Nevertheless, so take a look. Is there any difference? Take a look at these two things. This slope posterior and this slope posterior. On the right, we have no correlation. On the left, we have a correlation.
Yeah, looks very similar.
Very
Yes.
similar, right? So this is how you would establish whether there is an important impact of, some parameter. So, what will impact this posterior will be the residual standard deviation, right? So if I simulate data with much higher standard deviation, so it's about 0.5 in this data. If I made it 0.9, for example, okay, the residual standard deviation, the posterior would become wider. Why? Because the uncertainty of the posterior depends on the variance components. Okay, so the more variance components you have, the more uncertainty you will get in the parameters. Now, most of the time in psycholinguistic experiments, the subjects are the main contributors to high variance. Items are generally very low variance because these are planned experiments that we usually run, and so they don't really change much. They don't cause much variability. Of course, you can make them cause variability by introducing variation in the items, right? That's up to you to decide if you're interested in that variation. So for example, in Potsdam, we are interested in individual differences, right? How do the individuals differ? We don't care about this average effect. This thing that we are looking at, by we, I mean I, okay? So I don't care about the average effect, right? Because it's a completely useless quantity for me. I'm more interested in how subjects vary from one person to the next. And these issues become very important, how to understand the correlations between their intercepts and slopes and so on. And these things have theoretical interpretations. So you can look at that later on. And there, the subject level variation is going to have dramatic impact on what happens, as I'm about to show you. Okay. All right, so are we good? This was a very helpful demo, I think, to show what happens if you remove some parts of the model, right? Now, what we typically do in my lab, at least, is that we generally fit this maximal model just because we can, right? But as you saw, it often doesn't really make much sense because the correlation parameter is it's just the prior, If you don't have any data, you're just going to get back the prior. You didn't learn anything from that modeling, right? So you can decide to simplify your model, and that's okay too. Okay. All right, so I've already talked about all this. This is just notes for you guys. And so one other thing that you can do is that you can examine the predictions of the model by using the posterior distributions by back transforming them into the millisecond scale, right? So how does that work? So let me quickly explain this point to you. Let me see how I can do this. My iPad is unfortunately not working. So what I'm going to do is I'm going to write now and show you. So, my model is like this. The model says that my reading times RT are a function are coming from a log normal distribution with some alpha parameter, then some intercept adjustment for subjects, and slope adjustment for subjects, and then I've got my beta parameter, right, with U2 and W2 for items multiplied with the predictor, and then the residual standard deviation is sigma, etc., right? So what's interesting here is that because this is a log normal, my alpha parameters are now going to represent the reading times on the log normal scale. If I want to get back to the millisecond scale, I just have to exponentiate the alpha, and the alpha will give me the mean reading, median reading time. Right? The exponent of the alpha gives me the median reading time, right? And so what I can do, if I want to know the effect of the relative clause manipulation, so for, remember, the object relative had a coding that SO was equal to +1, right? And subject relative had the coding that -1, right? That was the setup. So what I can do is, if I want to figure out the difference between object and subject relative clause reading times, right? How do I do that? I will take alpha plus beta, that gives me the average reading time in the object relative condition, OR condition, right? And alpha minus beta will give me the the median reading time, the median reading time for the subject relative condition, right? And so if I compute this and I compute this and I take the difference between them, OR minus SR, I get right? So I can get the posterior distribution of the difference between the two conditions on the millisecond scale. That is pretty cool. I can plot the difference on the millisecond scale because that's what I can interpret. As a human being, I'm not very good at interpreting what's happening on the log scale. Well, now I am because I'm experienced in this. But when you're starting out in life, you're not used to thinking about the log scale. So what we're going to do is we're going to extract the posterior samples from the model, right? Extract the alpha, extract the beta, right? Also extract the correlations and the standard deviations for later use. And then what I do is I can do various things. So first of all, let me move ahead a little bit, show you the average effect. I'll come back to these individual differences later. Yeah, here, right? So look at what I'm doing. Alpha is the posterior distribution of the parameter alpha, this alpha variable, and beta is the posterior distribution of that beta variable. That means I have 4,000 samples for each of those parameters from the model, okay? So all I'm doing is I'm computing the mean of the median differences by computing the exponent, as I just showed you, right? This calculation that I just did, I'm just doing it here, and this tells me that the average difference between the two conditions is 44 milliseconds according to the model, right? And so I can also plot the 95% credible interval of the difference, okay? So what this shows me is that the model says that the difference between the two conditions is about 44 milliseconds with an uncertainty of 5 to 85 milliseconds, so 95% credible interval. That's a very large uncertainty, right? What that is telling me is that this data, this experiment is a very small sample experiment. Today, knowing what I know, I would never run such an experiment because after doing all this hard work of collecting 42 subjects data, I get a lot of uncertainty on this interval, right? So I don't really learn a lot from this experiment. All right, but this is how I would now go from the log normal model to the millisecond scale by exponentiating, right? This gives me the posterior on the millisecond scale. This is incredibly cool, right? Because now I can talk about my problem on the scale that I understand, right? And when I publish the paper, I would report, if I were to publish the paper, I would report this mean with this credible interval. So that would be one way to go, you know? Okay. And if I had a computational model that predicts, difference between object and subject relatives, I could compare it with the model prediction. That's what we actually do in our research. Okay, so these are the mean effects, right? This is what most people are interested in. However, there's actually even more capability in this BRMS, in the STAN, and the Bayesian framework that we can exploit now. So remember, in the model that we were looking at, the maximal model that I was talking about, in the Bayesian model, in the Bayesian framework, in the Bayesian framework, I had said to you, today when I started out talking at 11:30, I said that there are 9 parameters in this model. I was actually lying. There are more than 9 parameters. There are 9 parameters plus 42 adjustments here to the subject intercept, 42 adjustments to the subject slope, and 16 adjustments to the item intercept, for the item intercept, and 16 adjustments for the item slope. So these are in the Bayesian framework. All these adjustments, each of them is actually a parameter. It has the same status as alpha and beta. This is different from Elmer. In Elmer, in the frequentist framework, these things, the U and the W's, U's and W's, they are not parameters. There's something called conditional modes that they calculate by integrating out the other parameters, the 9 parameters that they have. Okay, so this is a big difference, and it has interesting implications for us. It has important implications for us. The implication is the following. Okay, what I can now do is that I can use this model to derive predictions for the individual subjects and look at the range of variation that my subjects are showing. Not just that, I can also plot credible intervals of the range of the estimates for each subject. That is incredibly cool, right? So let me show you how that works. Right, so as I just showed you, what I did was that I extracted all the posteriors for each of the parameters. Here are the correlations, standard deviations, sigma, alpha, beta, right? And what I've done next is I'm visualizing here in this plot, I'm showing you the by-subject slope adjustments that I computed from the model. You can look at the code later on. It's pretty tedious to look at it, and we're kind of running out of time. But what I'm showing you here is something very interesting. The subjects are showing quite a lot of variation going from negative to positive in the relative clause effect that these people show. So some subjects are showing positive effects. That means they're showing the pattern that object relatives are harder to process than subject relatives. But there are a few subjects that seem to be showing the opposite pattern. This is not predicted by theory. Okay, so if you're developing a computational model of relative clause processing, you are in trouble with these subjects. You have no way to explain this behavior. You can only attribute it to noise. Okay, but if this turns out to be systematic, then you have an interesting problem. Either you have too little data. You know that you have too little data. How? If you just look at the credible intervals, the 95% credible intervals of these data, you see that they're very, very broad. This is on the log scale, right? So there's very sparse data from each subject, which of course is obvious because we have only 16 data points from each subject, 8 from each condition. It's almost nothing, right? So we have a lot of uncertainty. And so if I really was interested in understanding if there are systematic individual differences, then I would have to make sure that either I have better priors, more informative priors, or I want more data, or both, ideally both. So this has important implications, this individual differences has important implications for areas like aphasia, where you're more interested in the individual level behavior and not so interested in what the aggregate of the subjects actually do, right? This is a super important point. And so,
Can I ask you a question?
of course.
Sorry. Can you go back to the individual variation plot?
Mm-hmm.
Yeah. So is the 0 on the x-axis, is that the average slope adjustment, or is it the null effect, no effect of object versus subject?
Yeah, the number 0 here would represent the fact that there is no difference between the two conditions.
Okay.
Okay, if all, if both the conditions had exactly the same reading time, you would get a 0.
Okay.
Because I'm plotting the difference between the two relative class types here for each subject separately.
Okay.
Using the posterior distributions of each subject. Okay? That's when you look at the code, you will see how cool this is, that I can extract the estimate for each subject, the posterior distribution for each subject, and I can just plot it, So this is super important. And this is not something you can ever do with the Bayesian, with the frequentist framework, because you don't have a posterior for every subject, right? So what are you going to do? All right. So that was an important thing. And the average effect I've already discussed. So, as I said earlier, most people are interested in the average difference between object and subject relatives. So, or between any two conditions. Whenever you're studying these kinds of questions, you're looking at the average effect. But one thing you should think about is that what does the average actually represent? The average difference, what does it actually represent? It represents an aggregation of the behavior of all the subjects, right? This is not sufficient information to really understand what human beings are doing. You should also look at the individual level variation, and you should be able to explain it, right? So that's why, that's why statisticians like Spiegelhalter, he's a famous statistician in Cambridge, that's why he often says something like the following. He says that the average is an abstraction. The reality is variation. What lies behind that comment, I mean, he was talking about more in the context of clinical trials, right? So there it doesn't make a huge amount of sense to talk about somebody's survival probability, for example, in an operation or something, right? That's just an average over many data points in the past. For that individual person, what really matters is that conditional on their, prior health conditions, conditional on the type of surgeon operating. Is it a beginning intern, like a new surgeon, or is it an experienced surgeon? And many different conditions. Conditional on all that, the survival probability will vary quite a lot, right? So that's why the reality of variation is super important to understand. And the Bayesian framework actually allows you to talk about this in a sensible way. So I try to show you how that works, right? Okay, so this is what I wanted to get across to you, the importance of individual levels modeling, right? So right now we are working very intensively on this issue, trying to understand individual level behavior. One of my students is working on this. You can see our papers on my homepage on this. I can talk about that more if there's some interest later on, right? And what else did I want to do? Yes, I'm out of time now, but I had planned to talk about logistic regression today. But I see that Anna has already introduced this in yesterday's meeting. Is that correct? People are basically familiar with logistic regression now. Is that right?
Hope so.
Hope so. Right. So I guess I'll be there in the afternoon. Okay, so I can jump in again, Anna, if necessary. But I'm sure if they've seen your slides and your PDF, it seems pretty clear. And if not, I will have time tomorrow to cover this part of the lecture where I talk about logistic regression. If there are some questions, please feel free to ask me tomorrow morning. And once we are done with that, then I will switch to Bayes factors and start talking about Bayes factors, because that's a frequently asked question in these kinds of courses. So I will discuss how to do Bayes factors analysis. And then tomorrow, I think Anna will also give you complete her demonstration with Bayes factors analysis towards the end. So you will get to see how she applies them in the logistic regression setting. I will be discussing Bayes factors with log normal likelihoods and so on. So that's it for now. Are there any questions? I'm still willing to talk a little over time if you want. If there are any questions, any burning questions, otherwise we break for lunch now.
I have a just side question about the prior for correlation. So that is the AKJ prior optimal for the correlation matrix, then I mean, can we use the other good correlation matrix as the prior so that we can compare it sometime?
Yeah, of course you can. So what you can do is you can change the eta parameter and see how your posterior changes, right? So if you guys will just humor me for 1 second, okay? Just humor me for a second and just give me like 1 more minute to talk about this point. Let's go back to this model that I just fit, okay? And so what I'm going to do now is I'm going to change back to my original model with the full variance covariance matrix. I have to put a comma back in here. And notice what I'm doing here, okay? I'm about to change the LKJ prior. I'll change it to 1. Are you with me? Kihyo, can you see me?
Yes.
Right. So I'm going to change that prior and see what happens to my posterior. Now we are very familiar with our posterior, so we can compare, right? What happens? Oh no, this is wrong. Why? Why is this wrong? Why is it complaining? Because I don't have any correlations here, right? So I put the correlations back in, start running the model. See what I had done, I made the mistake that I added a correlation prior, but I didn't have any correlations in the model. So obviously the model will refuse to fit, right? So I just fixed that. So let's give it a few seconds and then we plot the posterior and we take a look at what we get. Of course, it's going to complain again about diagnostics, but it's okay. While this model is fitting, I want to tell you something very interesting about this particular relative clause data. The effect, the effect of the relative clause difference that you're seeing between 5 and 85 milliseconds is driven entirely by 3 subjects. 3 out of the 42 subjects are showing unusually large differences, up to 400 millisecond differences, okay? And those are the extreme effects that are driving the average effect. If I remove those 3 subjects, I get the whole distribution shifting towards 0. This is one of the most robust results in psychology, in psycholinguistics. I mean, that object relatives are harder to process than subject relatives. But in this data, the effect is very sensitive. It's dependent on these individual level variations between subjects. There are just 3 subjects that are driving the effect. Super cool fact, right? Okay, so let's take a look at what happens to the posteriors. So now I've defined uniform priors, okay, on the correlations. Basically, that's what the LKJ prior is doing. So you see that the posterior for the subject correlation doesn't change much. That's because the prior is pretty uninformative and there is sufficient data to estimate the correlation. So I'm still getting a similar correlation. But look at the correlation for the items now. It has changed completely, right? And it's changed because of the change in the prior on the correlation LKJ parameter. I changed it from 2 to 1. So this is how you can study the impact. So the thing is, the issue here is that no matter what prior you choose, you will just get an uninformative result because the range of variation will remain very high because we just don't have any data to estimate this parameter. It's too difficult to estimate, right? So whichever prior you use, look, the posterior still hasn't changed much here. It's about the same as before. So everything else remains pretty much the same. And like I'm in a 0 information situation for this correlation. But I can study yeah. And so we can also do another thing. Sorry, let's just do this. Now this is becoming fun, right? Let's just do this. Let's change the correlation to something wild. Let's make it 10, okay? A correlation of 10 would be what? It would imply a much tighter prior, right? It would imply a much tighter prior on the correlations. Let's see what happens when I do that. So what I'm doing right now is a sensitivity analysis on the correlation parameter. This is what I'm doing. This is what I actually do in real life, right? So you do this systematically, one by one. If you want to know the impact of a particular prior on all the inferences that you're interested in, then you play with the prior to understand the impact of increasingly informative or less informative priors, and then decide, what makes sense for you. So, but what I typically do when I publish my research is that I always report the sensitivity analysis somewhere, either in the paper or I report it inside supplementary materials online, so that the reader knows, what the impact of the prior is on the parameters. And of course, when I'm working in a particular class of problems where I really understand what the experiment design is, I repeatedly work with similar designs, over many years, then I already know before I fit the model, I know what the impact of the priors is going to be. So sometimes in those special cases, when I really understand my problem, I don't need to do sensitivity analysis because I've been doing it for years for that particular problem. And so I know that there won't be much effect of the prior on the posterior. So let's take a look now. Let's see what we get. So now I have created a very tight prior centered around 0. Do you see this? This is so cool. So see what happened now. I've never done this before, by the way. Okay, this is the first time in my life I'm doing this. I made a tight prior centered on 0 for the correlation. Now this prior is overly informative. It's excessively informative. And that's why now the posterior is centered around 0. This is purely driven by the prior. And notice that the subject intercept slope correlation has also shifted to the left towards 0. That's because of the tight prior. Right? If I change that eta parameter to 100, I would be bang on top of 0. Right? It will get closer and closer to 0 because the prior is controlling the posterior now. Right? So that's a good demonstration. Okay, shall we stop now for lunch? All right. So I'll see you guys in 1 hour. I'll come back and I'll be online. I'll be there all day. So I'll be listening in. So I'm going to stop recording.